Modern polymer manufacturing operates at speeds exceeding several hundred meters per minute. A material web passing under these lights offers only milliseconds for surface modification. To print on or bond to these chemically inert plastics, the surface must be activated. This requires creating polar functional groups, embedding oxygen-rich molecules into the top few nanometers of the substrate so adhesives have something to grip. Achieving this inline is an exercise in manipulating fluid dynamics. Applying raw heat melts the substrate. Applying reactive chemistry alters it. The engineering tension here is strict. The system must deliver a continuous, highly stable pool of oxidizing radicals directly to the surface without exceeding the material's tight thermal budget. Every reaction at this boundary layer is dictated by the equivalence ratio, the exact stoichiometric proportion of fuel to oxidizer present at the moment of impact. Mastering this delicate thermal and fluid balance separates precision industrial processing from uncontrolled combustion. It requires heavily engineered burner architectures. The most basic architecture is the atmospheric, or open burner. These systems operate entirely at ambient environmental pressure. They work by forcing fuel through a nozzle, which naturally entrains the surrounding ambient air to form a free, open flame jet. As visualized in this diagram of an atmospheric nozzle, the chaotic entrainment of ambient air and fuel creates an unstructured thermal pulse. This rapid flash of heat and radicals is enough to desorb weak boundary layers off the material. Because they rely on surrounding air, these burners are mechanically simple. They are deployed on high-speed film webs requiring low capital expenditure and only modest increases in surface energy. But ambient air is unpredictable. This setup offers no independent mechanical control over the equivalence ratio, the bulk velocity of the gas, or the radiant heat flux hitting the substrate. Without independent control over the exact ratio of air to fuel, the chemical output fluctuates. Applications requiring uniform chemistry, handling thick substrates, or demanding adhesion standards. To achieve strict chemical uniformity, industrial lines scale up to power or forced air burners. These systems introduce air using external mechanical blowers. In this forced air cross-section, mechanical blowers decouple the air supply, regulating measured air and fuel inputs. Managing this feed dictates exact stoichiometry, replacing chaotic entrainment with a structured, laminar, tunable flame profile. This pressurized environment drives a steady reaction, sustaining much higher and more uniform heat fluxes directly across the treatment window. This is the required architecture for continuous industrial lines handling thicker or slower-moving substrates that demand deep, consistent activation. Taking mechanical command over stoichiometry transforms a reactive burning process into a tightly controlled, predictable processing space. For heavy-duty operations, even a forced air system requires tighter fluid control. This is achieved using complex internal nozzle geometries, specifically swirl vanes. Inside this nozzle tip, fixed geometric vanes physically twist incoming gas, inducing azimuthal momentum. This rotation drops central pressure, creating a recirculation zone, a highly stable spinning vortex of radicals locked inside the flame core. Instead of a direct blast of heat, this recirculation constantly mixes the reactants, homogenizing both the thermal and chemical field presented to the moving surface below. For an inline manufacturing process, this means the radical population stays steady for hours, enabling reproducible functionalization without requiring frequent manual adjustments. Designing these vanes requires rigorous computation. Engineers rely on Reynolds average Navier-Stokes equations paired with realizable K-epsilon turbulence closures to simulate the physical properties of the swirl. These models prove that even microscopic changes in the nozzle's wall roughness, or the angle of the vanes, will physically shorten or shift the extent of the recirculation zone. Watch how a purely chaotic fluid field hits the vanes and instantly organizes into a highly stable, spinning vortex column. Mechanical induction creates order. If a design is taken from a test rig to a factory floor without accounting for these specific velocity shifts, the flame will warp, creating severe downstream hotspots and cold wakes. Calculated correctly, exploiting azimuthal momentum mathematically solves the problem of radical depletion, securing an even chemical coat over high-speed substrates. Bulk flame stabilization solves uniformity, but highly sensitive substrates require spatial precision. This shifts the engineering focus toward microjet architectures. Rather than a single continuous flame front, these systems use distinct arrays of microscopic jets distributed across multiple fuel rows. Segmenting the treatment area this way minimizes the global thermal load, allowing thin or heat-sensitive polymers to be treated without warping or melting. Because the rows are isolated, operators can tune the local equivalence ratio independently for each one, creating tailored, spatially patterned chemistry across the web. Predicting how dozens of microscopic flames interact requires detached eddy simulation. This technique maps the highly complex velocity pulsations occurring in the aft region of the stabilizers. In this top-down heat map, we can track the distinct microjet supply rows. The specific number of rows and exactly where the holes are placed strongly dictate the mixture formation, preventing the adjacent jets from thermally interfering with one another. When a manufacturing line demands strict spatial selectivity or highly constrained global substrate heating, multi-row microjets become the mandatory architectural choice. The final vector for optimization looks past the fluid dynamics and changes the chemical environment itself, typically through hydrogen-enriched modified fuels. Spiking the methane supply with a high fraction of hydrogen alters the oxidizing radical pool hitting the surface, while reducing carbon dioxide and nitrogen oxide emissions. But this enrichment has immediate physical consequences. Hydrogen burns hotter and faster, heavily altering the flame's thermal profile and its visible emissivity. This comparison matrix highlights the resulting problem. Standard optical flame detectors rely on specific rectification signals. They easily read a standard methane flame, but they are blinded, failing to register the altered luminosity of a hydrogen-enriched fire. More critical than the sensor blackout is the mechanical danger. High flame speeds create an elevated propensity for flashback. Flashback occurs when the burn velocity outpaces the gas flow. The reaction reverses direction, collapsing backward into the burner cylinder itself and destroying the equipment. Tuning the chemical pool via hydrogen enrichment offers excellent surface activation and lower emissions, but it cannot be implemented without a complete, simultaneous overhaul of both optical monitoring and physical flashback prevention hardware. Selecting the right burner architecture is an uncompromising optimization of 4 variables: surface chemistry, the material's thermal budget, spatial control, and inline safety. Atmospheric systems have a strict use case. They belong on high-speed film webs, where the goal is low capital expenditure and only modest increases in surface energy. Forced air and swirl systems are mandatory the moment the process demands strict uniform chemistry and exact thermal control across broad, thicker webs. Advanced patterned activation requires microjet arrays, which rely entirely on rigorous computational fluid dynamics to prevent thermal excursions. Industrial flame treatment is a precise, mathematically validated discipline, engineered at the strict boundary layer of fluid dynamics and radical chemistry.